All right, welcome to The Explainer. Today we're tackling something huge in the industrial world, a safety standard called API 521. We're going to break down exactly how engineers figure out, what could possibly go wrong with pressure and how they stop it from turning into a total disaster.
So let's just jump right in with a big question. What's that one thing, that invisible threat, that can take a massive industrial plant and, turn it into a pile of junk in the blink of an eye? What are we really up against here?
That's right. It's overpressure. It's this massive, sudden spike in energy that can just tear pipes and vessels apart. And there's basically one rulebook, one essential guide that tells engineers how to stop that from happening. And that's API 521. It's all about designing systems to safely handle that pressure.
Okay, so before we even get into the nitty-gritty of what can go wrong, we have to talk about the ground rules. There's this one core principle that keeps everything realistic. And honestly, it's the foundation for everything else. It's called the double jeopardy rule.
And here's what it boils down to. The rule says you don't have to design for two or more unrelated bad things happening at the exact same time. And that word unrelated is everything. It's all about focusing our energy on what could actually happen, not some 1 in a billion chance scenario.
I mean, think about it like this, right? You're not going to build your house to survive a meteor hitting it and a massive earthquake happening at the same time. It's not a credible risk. The whole point of safety engineering is to be smart and rational, not to prepare for literally everything at once. And this is a perfect example of that. So a fire starting, at the exact same moment, a totally separate tube bursts? Nope, that's double jeopardy. We don't worry about that combo. But what if a fire starts and it gets so hot that it causes some nearby equipment to fail? See, that's different. That's a domino effect. It's one event causing another, and that is absolutely something we have to plan for.
Okay, so now that we have that double jeopardy rule locked in, we can start doing the real work. We can start asking, what if? We can finally dig into the common, credible things that could actually cause an overpressure event. And API 521 gives us a great list to start from. Here are 4 of the big ones, the classic what-ifs that engineers look at all the time. A blocked pipe, a valve that gets stuck, an external fire, or a tube bursting inside a heat exchanger. For today, let's really zoom in and take a closer look at those last 2, fire and tube rupture.
All right, first up, the external fire. This is the one everyone can picture, right? The most dramatic hazard you can imagine at a plant. So what actually happens when a big tank full of liquid gets engulfed in flames?
Well, the science here is pretty straightforward, but also kind of scary. The fire is just pumping a ton of heat energy into that tank. That heat makes the liquid inside boil like crazy, creating a whole bunch of vapor. And since that vapor has nowhere to go, boom, the pressure just shoots through the roof. It's a textbook overpressure situation.
So you might be wondering, how do you even calculate something as chaotic as a fire? Well, engineers need a rule of thumb, a practical way to approach it. API 521 gives them this number, 7.6 meters, or about 25 feet. The idea is that for a big pool fire, the most intense heat is really hitting the bottom 25 feet of a vessel. So for the calculations, that's the zone they focus on. It's based on real-world data about how these fires behave.
Okay, let's switch gears to our second case. This one is totally different. The danger isn't coming from the outside in, it's coming from the inside out. We're talking about a tube rupture inside something called a heat exchanger.
Imagine this. You have a bunch of small tubes with high-pressure stuff flowing through them, and they're all sitting inside a bigger, low-pressure container. Now, what if one of those high-pressure tubes just breaks? All of that high-pressure fluid floods into the low-pressure area, and it happens fast. We're talking almost instantly, like a shockwave of pressure. And that's the core problem, right? The big outer shell just isn't built to handle that kind of pressure. So the whole design has to have a plan to protect it from that sudden, massive rush of fluid coming from the broken tube.
To make sure they're being extra safe, API 521 makes engineers assume the absolute worst-case scenario. They have to pretend the tube didn't just crack, it got sliced clean in half, a guillotine failure. Then they have to assume the high-pressure stuff is gushing out of both ends of that broken tube. And on top of all that, if any of that liquid turns into gas or flashes, they have to account for that too, because that expands and makes the pressure problem even worse.
All right, so we've got fires, we've got tube ruptures, we've got blocked pipes. We have a whole list of credible ways things could go wrong. So what now?
How does an engineer look at all these different problems and decide which one to actually design the safety system for?
Exactly. You've done all this homework, all this what-if analysis, you've got your list of credible events. So where do you go from here? This is the moment where all that theory turns into an actual piece of hardware, like a safety valve that's going to protect the equipment.
And this is probably the most important part of the whole process. You absolutely do not add up all the problems. That would be like double jeopardy all over again. Instead, you do the math for each scenario separately. You figure out how big a relief valve you'd need for the fire, how big you'd need for the tube rupture, and so on. Whichever one of those requires the biggest valve, that single worst-case problem, that's what we call the controlling scenario.
So yeah, this really lays out the whole game plan step by step. First, you use double jeopardy to weed out the impossible stuff. Then you analyze every credible scenario you're left with. After that, you calculate the relief needed for each one. Then you line them all up, find the biggest one, your controlling scenario. And that's it. You size your safety device for that one case, and you're done. So, at the end of the day, what is a strong safety design? It's not about being paranoid and trying to protect against a meteor and an earthquake at the same time. It's about being smart. It's about a logical process of finding the realistic risks and then building a solution for the absolute toughest one you might face.
You know, this whole way of thinking, identifying credible risks, calculating their impact, and then designing for the single worst case, it's not just for industrial plants. It's a really powerful way to think about safety in any complex system. Which kind of leaves you with a final thought, doesn't it? How does knowing about this methodical process change the way you look at safety in the world around you?